So this video is about the second derivative test, and more specifically, what the second derivative test is telling us. So to figure this out, I'm going to draw a function with a relative maximum point at x equals c. So using our calculus knowledge, we can figure out many things about this function. So first off, we see it starts off very positive, then it becomes less positive, then it becomes even less positive, and then at x equals c, it becomes 0. So the slope of the tangent line is equal to 0 here. Then the function becomes negative, more negative, and even more negative. Now, what does this tell us? Well, because at the point x equals c, the slope of the tangent line is equal to 0, this means that f prime of c is equal to 0. And because as the function continues, it becomes more negative, this means that f double prime of c is less than 0. Now we can do a similar process for the relative minimum of a function. I could draw one better than that. Okay, so here we have a function with a relative minimum at x equals c. Now, using our calculus knowledge, we can figure out that it starts off very negative, then it becomes less negative, and then even less negative, and then at the relative minimum, the slope, or the slope of the tangent line is equal to 0. Then it becomes positive, more positive, and even more positive. Now, because the slope of the tangent line at x equals c is 0, we once again know that f prime of c is equal to 0. And because as the function continues, it becomes more and more positive, we know that f double prime of c is greater than 0. Okay, so how is this knowledge important? Well, let's go over the conditions for the second derivative test. For the second derivative test to be applicable, the first derivative, or in this case f prime of c, must be equal to 0. Secondly, for the second derivative test to be applicable, f prime must exist in the same neighborhood around x equals c. Lastly, for the second derivative test to be applicable, f double prime of c, or more broadly, the second derivative, must exist. In other words, the function that the second derivative test is being applied to must be a twice differentiable function. So a couple other things that we know about the second derivative test. If the second derivative is less than 0, this means that the function has a relative maximum value at x equals c. This was shown in this example. This leads to the conclusion that the function is concave down. In addition to this, if the second derivative is equal to 0, this means that the results are inconclusive. If the results are inconclusive, we do not know whether the function has a relative maximum, relative minimum, or neither. Lastly, if the second derivative is greater than 0, as shown here, note that the function has a relative minimum and is therefore concave up. So let's look at an example. Let's say we have a twice differentiable function, which is h. And for the sake of this question, let's assume that the derivative exists in a neighborhood around x equals 8. So we have h of 8 equals 5, h prime of 8 equals 0, and h double prime of 8 equals negative 4. And we have to find whether the point 8, 5 is a relative maximum, a relative minimum, or there's not enough info, or in other words, it's inconclusive. So take a minute, pause the video, and unpause it when you figured it out. Okay, so if you did this question correctly, the answer is relative maximum. This is because the second derivative test is applicable here, considering that h prime of 8 is equal to 0. We assume that the derivative existed in a neighborhood around x equals 8. And because h prime of 8 is equal to negative 4. Because the second derivative is less than 0, we know that the function has a relative maximum, as shown here. And because it has a relative maximum, it's also concave down. So we know that relative maximum was the correct answer. All right, thank you for listening. Have a good day.